Video, start the video. There we go. All right. As is the case with so many videos that I do on the fly, the minute I stop the video and put on, upload it, record it, I realize I forgot to say some things that I think were useful. So I'm doing a little addendum to the calculus. What was it? The graphical visual presentation, trying to get us to see things from a graphical perspective. Not working symbolically, but just visually with numbers. And so we did one with the cubic. We talked about point of inflection and graphing form. And I wanted to point something out that I didn't. So I'm back to the cubic. And let's just talk about cubics with the A coefficient being positive. So there's three types. There's one that's always increasing, one that has a slope of 0 at the point of inflection, and one with a negative slope at the point of inflection. It gives us three different shapes for cubics. There's something they all have in common, however. At the point of inflection, you have a minimum slope. So we're increasing more quickly on the left, more quickly at the end behavior here, and in between, we're increasing at the least amount. Slope, the one in the middle here is 0. Everywhere else, it's positive. Right there, it's 0. And this is the most negative slope, the most negative change in the y values at any place on that curve. I think I might have mentioned in the last video that you can think of these points of inflection. I like to use Grandma on Route 91, an analogy for everything I do in calculus. You can think of Grandma driving north, her velocities are positive. She stops, she turns around, starts heading faster and faster south, maybe sees a cop, decides to slow down, forgot something at home, turned around again, I don't know. But where was I? I just wanted to look numerically at some of these situations. And oh yeah, the velocity. Yeah, you can think of Grandma as slowing down, putting her feet on the brakes, maybe putting her foot on the brake, and then her foot on the gas pedal, something like that. A wind machine pushing at her. Some kind of force is applied in this situation, and so I should have thought about this a little bit more before I started filming. I'm a little tired. Okay, so let's get to what I really wanted to show you. And that is the fact that in calculus, we look at the equation line tangent to point of inflection. And many years ago, I put cubics in graphing form and just recently realized that it was there all along from this step, but it's not in the textbooks. Why it's not in the textbooks, I don't know. Maybe because people don't put things in graphing form for cubics. I think we should be. I think it's more important than rational root theorem, certainly more important than working with synthetic division, finding the roots. This is a very rich calculation for pre-calculus because we can see the interplay of rates of the different component parts and see how those affect, max and mins, why they come into play. Anyway, let's go and do just a couple of quick things from the calculus standpoint. And you algebra tours, it doesn't matter, you're going to do this eventually, so it doesn't hurt you to hear it. So we're just going to take derivative, and which helps us find the slopes at any instant, 6x squared plus 12x minus 10. And then the second derivative gives us that sense of where concavity changes, 12x plus 12. We set it to 0, and we can quickly see algebraically that our critical point is -1 for this cubic. Okay, so what else do we know about that cubic? Well, might as well start graphing it. So we know on the y-axis from our work already, we're at a height of 1. We know we're going down at 10 to 1. We don't need calculus to learn how to do that. We probably have already done it with the quadratic in class. And then these two terms eventually swing it in that direction. And we can look from the negative standpoint, but there's symmetry. So that's what our cubic looks like. And so we know that at 1, we can find -1, excuse me. No, that was a y-intercept. So, I got to go back and do this again. Thought I was working with a point of inflection. Wasn't. Okay, I don't want to have to do this video again. So here we are. So at 0, we're at 1. There we go. And we're going down at 10 to 1. We'll make that 10 to 1. I guess I got to do something like that. And then at -1, I'm going down at what we can find out by plugging it into the first derivative. I did that, -16. So we're going down more steeply here at -1. And so we can begin to see the curvature like so, the curvature like so. So there's our cubic. All right, there's our cubic. And this is the point of inflection. And the equation of the tangent to the point of inflection is minus 16 x plus 1. Well, I'm here, right? I didn't label that point. So I got to find out where I am. So where I am is the original position function. So if we put -1 in, we get -2 plus 6 plus 10 plus 1. All right, 17 minus 2, 15. So we're at a height of 15 at -1. So at -1, we're at a height of 15. And we're going down at 16 to 1 at that instant. So let's get this down. So we're going down at 16 to 1 at that instant. All right. I'll put it to 1. Let's see, what are the points that I want to make? Oh, yes, looking at the numbers here. I hope you see a 3-to-1 ratio there at the point of inflection. There's a reason for that. You want to go look at the completing the cube video in order to understand that from a geometric standpoint. And I think if you think about the cubic having no volume at a certain instant, then the rate of change there is going to be unique. It's going to be unique because there's symmetry to cubics. So rates of change are going to be somewhat in opposition to each other at different places here. But there's definitely some symmetry. And so that moment when that cubic is 0, that's a special rate, okay? Now, plugging in -1 into this term, this is what I really wanted to mention, was a -2 to 1. And so hopefully, I'll make sure that I don't have to do this again. Yeah, you can see everything. Algebra 2ers, we've probably done a lot of work with quadratics at this point, and I hope you recognize that relationship only happens one time. That's at the vertex. And the vertex of a quadratic gives us a y value that is either a min or a max, right? And that's what we're talking about. We're talking about rates of change here as being minimum and maximum. That's a minimum rate of change. If I was to look at a negative cubic, point of inflection being here, okay, then this is always going down. This is going down least quickly. So that's actually a maximum rate. And if we were going to put a couple of points together and compute slope, this would be the biggest M we've got. I know it's negative, but it's the biggest one. All right, -2 is bigger than -10. Right? We might be going down at 10 to 1 here and maybe 2 to 1 here. I just made up some numbers. Okay, and so with a cubic, the point of inflection has a particularly important rate of change at an instant. And we can see that with that 2 to 1 rate. I also thought it would be useful to put this in graphing form now. I mentioned it earlier at the beginning of the video. And so I think I've already done that work. This board's kind of filled up now. So let's go over here where I had done this before, different color marker. I had lunch, came back, and now we're looking at this and I can see everything. Good. So same function, right? Here's the rate of change and the location, the point of inflection right here, going down 16 to 1. Okay, what else can we see? That if I wanted to put it in graphing form, well, I've already got the 2. I know the highlighted moment is -1, and that's at a height of 15. So if you multiply this out, you've got that. So why is it a graphing form? All right, well, let's look at it. What can we see from this? We can see the linear function. Oh, right there. That's going down at 16 to 1, and it passes through the point. The points here. Let's see, vertex, point of inflection. -1, 15. So that's highlighted. That's the most important point on the graph, and it's being highlighted. Okay. What else do we have? Okay, we got a positive cubic, so we know it's going up. We know it's going down. Okay, so we got the graph. There it is. Yeah, and I suppose you put a 0 in, and it's not going to be too hard to find your y-intercept. It's not hard to find these values either. Right? This, from a non-calculus standpoint, comes from, let me remember here. So this is often referred to as HK. just like HK. Well, it's not often. I don't think anybody's putting cubics in graphing form, but we'll call it HK, just like the vertex of a quadratic, highlighting horizontal and K for constant, KAT cat. So how do you find these X values? Not hard. Without calculus, it's H, which is in this case -1, plus, because we're moving to the right this time, the square root of -m over 3a. I think I might have done that before. So let's see, C minus 3ah squared gets us m. All right, which is -16, which we could have gotten from the calculus standpoint. But C is -10, so I did that up here. -10 minus 3 times a times h squared, and there's your -16. That's the same thing. Equals -16. Kind of looks like quadratic formula kind of work. I'm sure it's a formula. We're working with it. And so that gives us our rate of change if we didn't want to do it from a calculus perspective. Minus b over 3a, again, gets us that x value very quickly. What did I want to show? Oh yeah, I thought it would be interesting to see where the number 2 comes from a graph like this. So I put the number 4 in. I hope I got the same function here. So 4 got me 185. All right, so how do I get this number 2? Let's look at it right now, because I got all this, right? So let's say I just had this graph and I wanted this. Well, I could use -1, 15. -1 gets me 15. Changing at 16 to 1. So I could create that very quickly from what's in front of us. So how do I get that a term? Well, I know one thing from previous work, that if I'm looking in a table, let me get a table of values. -1 and it gets me 15, and 4 gets me 185. Well, it's a beautiful little conversion, right? Because if you put a 4 in here, 4 plus 1 is 5 cubed. 125 units doesn't work. I don't get there by adding 125. I got to get that out of the picture. And the kicker here is, you got to be careful, because if you put a 4 in here, you've actually gone down 80 more than, you've changed this calculation by 80 units. Right there. So what do? That takes me down 80. I'll go up 80. I'll just get that change out of the picture. Now I can come in and say, how far is it from 15 to 185? 170, if I'm not making a mistake. 170. 170 plus 80. Oh, 250. 250. And what's 250 divided by 125? There's your 2. Okay, so there's a lot going on here. There's a lot that needs to be looked at and understood. Well, that takes some critical thinking. So I hope that you, don't just breeze through this, but actually give it some thought. Try to digest some of the concepts. This is really a cubic with a slope of 0 at -1, 15. This is a linear function going through the same coordinate. And what happens when you add these two things together? Well, the rate of the linear is dominant locally, because that cubic's not changing. When you get near 0, the y values don't change much at all, but this is always going down at 16 to 1. So we end up getting something that's kind of a hybrid. And where are we turning? Again, where that slope is going down at the same rate that this slope is going up. And so we end up getting a slope of 0 right at that instant. And it's when those rates are in opposition. All right, so lots to think about. All right, and I'll upload this now to YouTube, and maybe somebody will look at it. All right.